No questions?
There's a
Okay.
question on the chat that will these seminars be recorded if we have a class later?
It
Yes,
will be recorded,
and
yes.
posted on the ECED website.
All righty, I guess I should start.
Please
My friends, welcome. I hope that all you students out there, that you're doing well, that you're safe, and I wish you and your families the very, very best. We're all going through quite a bit, and let's just all hang in there and practice good things and help one another and stay safe. With that said, I'd like to begin the presentation by saying, if you have any questions at all about anything whatsoever, if you feel that I've maybe left something out or you'd like a little bit more detail, please feel free to ask, and because I'd like to answer every one of your questions. And if I can't answer all your questions during the presentation, I will certainly make myself available afterwards. You can even call me, and then I'll make sure that your questions get answered. All right, so I like to begin this presentation by conveying the idea that the age of intelligent systems has arrived. Now, when I did this presentation, when I first put it together years ago, I knew the driverless vehicles were coming because I had been working on them since the early 90s. Yes, early 90s. I knew the drones were coming because I had been working on them as well. I was waiting for this artificial intelligence revolution to take off, and I certainly had no idea that it would take off within the last 5 years or so. I mean, it has been an evolution, but certainly over the last 5 years, one can make a very strong argument that it has just taken off across planet Earth. And I can have a very long conversation with any of you if you're interested in talking about artificial intelligence. But I want to begin by saying this. I often joke with students and professors that controls is not artificial intelligence, but real intelligence. So I say that joking around, and I certainly don't want to get anyone too upset at my comment, but what is it that I mean by that? Controls has been around for quite a long time. It is a mature discipline. It is one of electrical engineering's original disciplines. And well, if you look at our society today, you look at the airplanes, the cars, emission control systems, temperature control systems, you see controls everywhere in our society, everywhere. All the driverless vehicle stuff, all the drone stuff, all the advanced semiconductors. This computer that I'm using has thousands, arguably millions of feedback systems within it. And without these feedback systems, this computer would not work properly. So that's why I refer to controls in part as real intelligence, because what we do in controls is we design a system to perform the way that we like using feedback and based on mathematical models. And there's a rigorous theory for controls that has developed over many decades. Now it's approaching almost 90 years or so. One might argue that this controls stuff really got started in the 1920s, 1930s. Now certainly it's been around for thousands of years. The idea of controls and feedback systems. So that's why I refer to controls as real intelligence as opposed to artificial intelligence. And a lot of the concepts that you find in artificial intelligence fundamentally have their roots in controls. So you see, I'm a little biased towards controls. All right, let's keep going. So we are living in revolutionary times. For the first time in history, now remember, I did this presentation, I made this presentation years ago, but the presentation holds, these facts hold even more so today. For the first time in history, we have at our disposal technologies that allow us to do tremendous things. I remember just, 15 years ago, where we were using the NASA supercomputer in order to design certain air vehicles or space vehicles. And just a few years after that, we were using our laptops in order to design these very, very advanced vehicles. So that shows the progress that we've made. And today's laptops, today's desktops, etc., we could design really, really complicated systems. And so because of that, that's why when you look around, we're seeing all these driverless vehicles, drones, and all of these intelligent systems. And it has just started, folks. It has just started. I think there is no way for us to really look 10 years into the future and see what it's going to look like, because there's so much involved, economics, social, etc., and so forth. But certainly the age of intelligent systems is here. There's a question?
Cutting edge.
Okay. If you got any questions, folks, just holler. Please holler. Don't feel embarrassed to interrupt me. I would love to be interrupted. Okay, let's keep going. So I want to thank all my students and everybody that's helped me have this wonderful, wonderful career. When I was a student sitting in your seats, I couldn't have dreamt of the things that I've had the opportunity to work on. I've had the opportunity to work on spacecraft, on high performance aircraft, on missiles that shoot down the aircraft. I've worked on laser weapons in space that shoot down missiles, and I've worked on a lot of friendly stuff too, managing resources, renewable resources. One of my coolest projects was working with Eleanor. Oh gosh, what was, my brain just froze. Well, to put it short, she won the Nobel Prize in Economics, I believe in 2007. And we called her Lynn Astrom. And so we worked on renewable resources, managing fisheries, et cetera, and so forth. And having the opportunity to work with her was just amazing. And I could go on and on with these types of stories, but I got to move on to the specifics of the presentation. But folks, I beg you to really think hard about what you want to do in the future, dream a little bit, and start planning yesterday. All right, because there is so much going on right now. There is just so much. This crisis that the nation and the world are going through, it's getting our creative juices going. There's so many people thinking about, okay, how we can do this better and that better and this better, et cetera, and so forth. And so I'm very, very, very optimistic about what we will see on the other side of this very vicious pandemic. Okay, so what is controls? Where is controls used? And I'll tell you right now, it's everywhere. Everywhere you look, and it doesn't just have to be the air conditioning system that you're experiencing here in Arizona, which is a really nice thing. all right? But it's everywhere. Semiconductor furnaces. Folks, this pandemic that we are going through and fixing it, getting people vaccinated and controlling the growth of cases and certainly the death rate, et cetera. Fundamentally, folks, this is a controls problem. It is a controls problem. And so I could talk to you for hours on end about the importance of testing, because if you don't test, then you don't know where the problem is and you cannot fix it. And the same holds not just for this pandemic, holds inside of an airplane, inside of a semiconductor furnace, a robot, a driverless vehicle, etc. I'll be talking about the courses, the relevant courses, the faculty involved, the job opportunities. And I think I've already mentioned that there's an ongoing technological revolution. Please don't miss it, folks. What I mean by that is often when you're in the middle of something, you don't see it and you might not fully appreciate it. There are many ongoing technological revolutions taking place right now. And let me say the following. Not only can we now edit genes, but folks, we have been repairing organs and growing organs in the lab for years. Now, I've had the opportunity to work on all different sorts of rovers and spacecraft, and it's been amazing. Very cool. I would have done it for free. I really would have. But this organ growth and organ repair is cool on another level. And even though you're electrical engineers, I assume most of you are they're all electrical engineers out there, right? And you might be thinking, hey, what does this organ growth have to do with me? Folks, it will impact all of you. And I would guesstimate right now that, at least 30% of you will be working in that arena at some point in the future, maybe in the near future. And you may be developing instrumentation for that arena because there's so much to be done. All right, there's a lot of cool stuff going on, folks. I want you to think about it. Think about the robots that are coming now for manufacturing, for helping elderly, for helping soldiers, etc., for going into environments that we don't want people to go into. For example, after the Fukushima disaster, some primitive robots were sent in there because there was a lot of radiation. And what we will see in the future, in the next 5 to 10 years, is really going to be incredible. All right, what is controls? So I usually use this block diagram to indicate or to describe what controls is about. Here, P represents the plant or the physical system or process that we're trying to control. And folks, we can control anything in principle that has inputs and outputs, and assuming that we can measure the outputs. Measurements are very, very important in the world of controls and in the world of making intelligent systems. Fundamental to intelligent systems is feedback loops. All right, if you don't have a feedback loop, then it probably is not an intelligent system. All right, because at the heart of intelligence, and many scholars have defined this, is feedback systems and feedback loops. And these feedback loops provide for corrective action. So getting back to this feedback diagram, this plant is the physical system or process or social system that we're trying to control. The controller K is what we want to learn to design, and that is what you will learn how to design in the classes that you will take with us, like EEE 480, 481, et cetera, and so forth. All right. And what are some of the issues associated with this control problem? Well, we see that there is a desired output on the left. That's the R, or the reference command. And on the right is Y, the actual output. And in short, what we want is we want to design this controller K on the basis of a mathematical model for this plant P, such that the actual output Y tracks or follows the desired output R. All right, so I often use the example of a temperature control system because we here in Arizona, we identify with that quite well. And I also use the example of a cruise control system in a car because we've all been in cars and we've seen perhaps these cruise control systems working. And those are the simplest examples that I can give, but I can get much, much more sophisticated. We could be talking about a spacecraft going to Saturn, and we have a very complicated cruise control system for the spacecraft. And now we're traveling, maybe 25,000 miles per hour, and we want to control lots of things on the spacecraft. But what are some of the issues? There are always disturbances present. That's what the DI and the D0 represent. There's always sensor noise present. When you feed back a measurement, whenever you feed back a measurement, folks, there is going to be sensor noise. And so the challenge that I put forward, namely, how do we design this controller K based on a mathematical model for the plant P, such that the actual output follows the desired output in the presence of these disturbances and sensor noise? How do we do this? How do we do this systematically? That is what controls is about. That is fundamentally what controls is about. And we use mathematical models based on the physics or the chemistry or the biology of the system. And it really doesn't matter to me what P is. Yes, all my degrees are in electrical engineering, but I will tell you that one of the main reasons I chose controls for a career is because I saw, I think probably as a sophomore, so I was a sophomore, and I saw, wow, this stuff can be applied to everything. Robotics, airplanes, distillation processes, chemical systems, biological systems. Oh yes, electrical systems, electromagnetic systems, etc. Antennas, smart antennas, and I could go on and on. And so yeah, even though I liked the other disciplines, even though I loved the other disciplines, I loved circuits, and I loved electromagnetic theory, and I loved signal processing. I really fell in love with controls because I saw that it can apply to everything. And folks, we have an artificial intelligence revolution spreading throughout the world. This is not a fad. This is here to stay. There's at least, I want to say 25 of the top 30 companies in the world, of the biggest companies in the world, are dedicating millions and millions and millions to artificial intelligence because they understand that it will allow the creation of amazing things. And I don't just mean driverless vehicles, drones, amazing robots, etc., and so forth. There's a lot more coming. Okay. Yes.
Professor, there is a question on the chat that can your plant be a complex adaptive system? So instead of trying to control, say a reaction wheel, you are trying to control the trajectory of an entire system of independent agents.
All right, so the plant here can be 1,000 robots that are trying to accomplish a mission. And if that's not complicated enough, okay, well, we can make it 100,000 robots, et cetera, and so forth. But yeah, the plant could be the economic system of the United States. The plant could be the economic system of the world. So I think that gives you an idea of what the plant can be. It could be, as I said earlier, anything that has inputs and measurable outputs. Okay? With that said, and thank you for asking that question. That's a good question. In the lower right-hand corner, there is a fab. It's an Intel fab. That is a semiconductor fabrication facility. To give you an idea of what's involved in one of these semiconductor facilities, these semiconductor facilities typically make about $1 million an hour profit. Okay, so I want to say it again. These semiconductor facility like this might make $1 million an hour profit. Okay, so in there you're controlling a bunch of processes, et cetera, and so forth, and you're trying to meet a certain customer demand. And so this is very, very complicated. There's a lot of uncertainty present. Let me say something about uncertainty. The main reason that controls was invented, the main reason for controls is to deal with uncertainty, to deal with uncertain disturbances, to deal with uncertain noise, to deal the reference commands, the desired outputs. They can even change. They could be uncertain. I mean, what if you have a missile that is trying to shoot down another missile? Well, one missile is moving, erratically, say, to try to escape the other missile, and so those measurements that are being gathered by the following missile, they are all over the place, and those measurements represent the desired output for the missile that wants to shoot down the other missile. So you see, even the desired output can be all over the place. And let me also say that the plant model, we never know the plant perfectly. We never know the plant perfectly. So therefore, there's another source of uncertainty. After Boeing or Intel spends billions of dollars developing a chip or developing an airplane, even 5 years, even just a few years after developing and deploying it, they will learn new things about it. Was there a question? Was there a question? Okay.
Yes.
Go ahead.
So, Professor, so what's the main difference between controls and systems engineering as a discipline?
All right. So systems engineering is very, very, very broad. Systems engineering might incorporate communications engineers, signal processing, digital signal processing. I mean, you can put in there image processing. You can put in there computer architecture, computer design, et cetera, and so forth. And yes, controls is in there as well. But certainly systems is a much broader area. Does that make sense?
Yes, thanks.
Okay, so systems is much broader. Controls is about trying to make a system. Controls fundamentally is about using feedback in order to try to make a system behave in a very precise way in the presence of uncertainty, like disturbances, sensor noise, uncertain reference commands, as well as uncertain or unmodeled dynamics. And what do I mean by that? again, we never know P exactly. We might have a very good model for it. We might have a model that is 100,000 lines of code that takes a week to run, you know, for just a few minutes. All right. But we never know the plant exactly. And so part of what we want to do as control engineers is to design for most reasonable possibilities. Okay. Before we got started, one of the students asked what was one of the coolest things, I'm paraphrasing, one of the coolest things that I ever worked on. If you look at the upper right hand corner, there's an image there. That image is of a spacecraft called JIMO, Jupiter Icy Moon Orbiter. JIMO was designed at the Jet Propulsion Laboratory. I was responsible for leading a team to design the control system. Again, I would have done that for free. The first spacecraft that they designed had solar appendages that were too big in order to meet the control specifications that they wanted. This spacecraft was going to be exploring Europa. And we're looking for life, folks. We're looking for life, right? And so it had to perform certain maneuvers and rotations in a certain amount of time. But because the solar appendages were just too big, it would take much longer to perform these maneuvers. And the people at JPL had to go back to the drawing board, and they didn't appreciate that, and they had to resize their solar appendages. So it was a pleasure working on that. I would have worked on it for free, even though my wife doesn't like me saying that. But that's just one cool area, okay, that I got to work on. And folks, you guys you have so many cool opportunities that you can take advantage of. I am happy for you and a little envious too, all right? Because I wish I was 21 years old right now. I'm a little past that, but I'm so happy for you. And you should be excited about the opportunities that exist for you. It's just a matter of planning, folks. Start planning. All right, let's keep going. So I gave the example of the cruise control system. There's a lot of pictures here. If you see, can you see, I think you could see my cursor, right? Can you folks? Anybody?
Yes, Professor. Yes,
All right.
Professor.
Okay. So if you see my cursor here you're seeing a two-stage to orbit system that I was very fortunate to work on with NASA. Again, something I would have worked on for free. This vehicle on top is a hypersonic vehicle. By hypersonic, I mean a vehicle that goes 5 or 10 times or 12 times the speed of sound. But it is an airplane-like vehicle. It's not like a rocket. It's an air-breathing, airplane-like vehicle. And so again, that was just so much fun working on it. And again, the reason for sharing this with you is because, folks, there's just so much cool stuff that you can work on. If you just go out and look and explore, there's just so much. This slide is very busy. You will have access to this entire presentation. I won't go into this slide. It gets a little bit too technical and a little too nerdy. We could discuss this in the future. Okay. This
There's a
slide is
question.
a little busy as well. I've already talked about some of this stuff. Here in this world of controls that I'm talking about, we design the controller on the basis of a model for the plant, on a base of knowledge, some knowledge of the disturbances, some knowledge of the noise, some knowledge of the reference commands. So we rely on these models because, folks, if you don't have models, then what do you design for? Okay, and so sometimes in the artificial intelligence world, they do stuff, and an assumption at the beginning is that they don't have a model. And so the first thing they try to do is develop a model. Now, our philosophy here in the controls world that we live in is, well, you do the best you can to use the physics, the biology, the chemistry, et cetera, and so forth to have a model, and then you use that model in order to design your control system. And then on top of that, you can piggyback artificial intelligence or certain convex optimization algorithms in order to make your control design smarter and in order to get a better model. All right, let's keep going here. Where is controls used? Okay, this is one of my favorite topics. I'll try to keep it fast. It's used everywhere. Controls is inherently multidisciplinary. So I worked on hypersonic vehicles. Folks, all my degrees are in electrical engineering. I never took an aerospace vehicle design class. However, I'm looking right now to my right. I have a bookcase, and I have probably more aerospace books and mechanical engineering books than many aerospace and mechanical engineers have. Why? Because I fell in love with this stuff many, many years ago, and I knew that I would be able to work in it. And so I just pretty much, when I needed to learn something, I just got all the books, not got a book, but got all the books. That was expensive, but it was, it's been fun. So where is controls used? This list, which goes on for several slides, is so impressive. It impresses me to date. Right now you can't see, but the hair on my arms is standing up. And that is because even now, after, oh my goodness, nearly 40 years thinking about controls and being involved in controls, I'm still excited about controls like I was when I was a young 18-year-old, 19-year-old undergraduate. And so you see, controls can be used for capital, where did it go? Capital investment. So that's economics and portfolio management. And I can just go on with different applications, folks. Medical applications, nuclear, in the ocean, public policy, and I could just go on and on. That's why I fell in love with controls. And let me say that this list that I made up, I made this list many years ago. I could easily make a list that is twice as long as this. It's a pretty amazing list. I think that that is pretty self-evident. Courses. Let me talk about the courses. All right. So for me, and for most of you, and you might not know it, but for me, it all began with circuits. I started circuits, and that's where you learn KVL and KCL, yes, and then you'll learn Laplace transforms. And that was my beginning. It was a beginning for me to understand what a circuit was and understand what a system was. And those tools that I learned in my circuits class, folks, I use them every day in the controls world that I live in. Now, when I was a student as an undergraduate, I didn't think that the thought processes and the analysis processes that I was learning, you know, KVL, KCL, loop analysis, mesh analysis, nodal analysis, and I could go on and on and on. But really it was a way of thinking. And that way of thinking is helpful and essential in controls. And certainly there was differential equations, and there was linear algebra, and then there was signals and systems, all right? And these were all very fundamental to laying down a foundation for controls. Students often ask, hey, should I take signals 2 before I take controls classes? My answer is this: take signals 1 for sure before you take controls classes. And it would be great if you can take signals 2 either before, ideally before you take controls, or at least at the same time. All right. And if you have any questions on this or anything that is related to this, I will be happy to talk to you certainly after the presentation at any time in the future for at least the next 20 years. After 20 years, I can't say anything because my mind might not be all there. All right, but for at least 20 years, I hope I can help you out. All right, now what are the main controls classes that we offer in electrical engineering? There's EEE 480 and EEE 481. I have taught both. I love teaching both of them. But for the past few years, I have mainly been teaching 480. And so the main faculty in controls are Dr. Jenny C., who's our neural network expert. There is Dr. Sakalis, who is our adaptive control expert. There's myself, Rodriguez, who's a very high energy, excited individual who loves many, many things. And I'm supposed to be the multivariable control expert. These are the main control faculty. And I'll be saying some more about the faculty. Let's see, I'm gonna just go just a little bit to give you a glimpse. There's also Dr. Lai, all right? And he mainly works on brain stuff, but let me say that Dr. C, as well as Dr. Sakalis, also work on brain stuff. And when I say brain stuff, folks, you know, there's a great deal that we know about the human body, but there's still a lot that we're still understanding about the human brain. And I know that in the next 10 years, we're going to learn more about the human brain. That is so exciting. So I invite you to dive into that arena and learn as much as possible, because there's going to be all sorts of job opportunities in addition to the obvious, which is brain-powered prosthetics. Okay? So, okay, I've said a little bit about the faculty. Let me go back to the classes. There's a question.
Professor, there's a question.
Go ahead.
So, Matt is asking that, Professor Rodriguez, in your intro, it says that you are part of the Intelligent Embedded Systems Lab.
That's
Are there
correct.
are there opportunities for undergraduate students to take courses in EEE regarding embedded systems at ASU? Additionally, are there controls on intelligent systems related courses at the undergrad level besides 480?
Okay, so 480 and 481 is really the basis for anything. If you want to, especially if you want to do advanced work, then these are essential classes. It bothers me sometimes when I see some students, they're taking some artificial intelligence classes, but if you don't have the basics of feedback systems, then you're really, really missing out on fundamentals. Imagine taking calculus without having, I don't know, trigonometry or pre-calculus. I mean, I think we would all say, no, that's just not possible. Well, that's how I see some of the classes that are being offered because they try to present very advanced material in a very, very, cut and dry formula or easy way, a cookbook manner. But this stuff is very complicated. It's very complicated stuff. And so these classes are the basics. Let me say something about these classes. If you were going to only take one controls class, then, and you should take all the controls classes, of course, but if you were only going to take one, then I would probably suggest that you take 481, because 481 has continuous time stuff as well as discrete and digital and embedded system type stuff in it. Now, 481 is supposed to be the more applied class, all right? In principle, one might argue it's supposed to be more applied. It's supposed to be the less theoretical class, and hence one might argue the, maybe even arguably the easier class. However, it has in it not just continuous time stuff, which is like Laplace transforms, but it also has discrete time stuff, which is Z transforms. And so managing all that together, you know, that takes some work. And so ideally, if I could advise you students, I would say take 480 first and then take 481. And most of my students have taken 480 first and then they go into 481. And let me say this, that there are students in taking 481, and 481 is their first controls class. And if my students that have taken 480 and they are now in 481 with you and you're learning controls for the first time, folks, you're at a big disadvantage, because students that are coming from 480 into 481, they don't just know a little bit about controls, they know quite a bit about controls. So there's my 2 cents on 480 and 481. Both are very good classes. I love both classes. Right now, 481 is taught by Ashfaq, and he was a PhD student years ago. He's now an instructor. He's a young guy. He's got a lot of energy. He's a wonderful guy, and so I endorse that class wholeheartedly. And then 480, that one is taught by me most of the time, and I love that class very much. Now, what are some of the more advanced classes? Well, at the graduate level, and folks, if there is one message that I really want to convey, it is the following. Get your master's degree, folks. No one has told me to say this. No one is paying me to say this. I have no stake in this, really. Get your master's degree, folks, because it will help you with your career immensely. And you should get your master's degree as soon as possible. If you can continue from your undergraduate degree and finish your master's degree right away, that is what I would advise you to do. All right? If that is not possible and you must work, then I understand. The word must is a big word, and I understand it and I hear it quite a bit. If you must work, folks, there are companies out there that will pay for your master's degree while you're working for them. and there are lots of managers and supervisors out there that will view you as an investment, and they want to help you progress, and they want you to get your master's degree because they know they need highly trained individuals. All right, but it is much harder going to school and working at the same time. Much harder. My wife did it, and she would tell you if she were here that she would have finished her degree right away, and she she's a very high energy engineer involved in many things, and she certainly would have said that she would have liked to have finished her degree rather than working and finishing the degree together. Although it was nice getting that degree paid for, etc., and so forth. All right, let me keep going. What are some of the graduate classes? There's 582, which is linear systems. Linear systems these days is typically taught by Dr. Sakalis. I've taught it many times. I will probably teach it in the future as well. Then there is nonlinear systems, 586. Certainly you need linear systems before you take nonlinear systems. Nonlinear systems, arguably, one can argue, is probably our hardest class. It's our most advanced class. It has the most advanced math in it. But as such, it will allow you to do the most advanced stuff out there in the real world, especially if you are interested in doing very serious artificial intelligence. Oh, and I forgot to say that our expert at adaptive control, that's Dr. Sakalis. I apologize to Dr. Sakalis. Yeah, he's our expert adaptive control person. Jenny C is our expert neural network, machine learning person. And like I said earlier, I'm the multivariable control person. If you got complicated systems with many inputs and many outputs, then you can talk to me, but you can talk to them as well because they deal with very complicated systems. All right, another class that our control students have taken over the years that I've taught in the past was transform theory. That's 550. There's also random signal theory, 554. That's where you learn about, that's where you really get your probability theory down really well, and you start learning about stochastic processes. And that's critical for advanced work in the world of systems or controls, or certainly artificial intelligence, because folks, there's always going to be random disturbances, random noise, random commands, all different sources of uncertainty that fundamentally are modeled probabilistically. Okay, there is also optimal control, that's 587. That class is often taught by Dr. Sakalis, and Jenny C has taught it. There's neural networks. That class is taught by Dr. C, Dr. Jenny C, and that's a fun class, and that is a class that I recommend everybody to take. Everybody should learn about neural networks today in this day of machine learning. When people say machine learning, they're fundamentally talking about neural networks, folks. All right, and so you really should take this 511 class. There is a filtering of stochastic processes. That's where you learn a bit about Kalman filtering. Oh, and I you know, goes figures. Go figure. I skipped over one class. Which one did I skip over? I skip over the class I teach, which is robust multivariable control that I'm teaching this semester. That's 588. And that's where you're dealing with multiple inputs and multiple outputs. And it doesn't matter to me. You can have 100 inputs and 100 outputs, or you can have 1,000 inputs and 1,000 outputs. Doesn't matter. The techniques that we learn in that class allows us to deal with very complicated systems. And then finally, there is adaptive control. And as I said or alluded to earlier, that is the Dr. Sakalis class. He's our expert on adaptive control. What are some other classes that our students have taken over the years? There's system identification. That is where, on the basis of inputs and outputs, so measurable inputs and outputs for a physical system, you try to figure out what the system is. So there you're trying to figure out a model in real time. Or it might not be in real time. Maybe you gathered these inputs and outputs and you're trying to figure out the model offline, okay? But it could be in real time. So system identification is a class that is typically, it has always been taught by Dr. Rivera in chemical engineering. It is a wonderful class. Most of my students and Dr. C's students and Dr. Sakalis students, and I by most, I mean, 99% of them over the years have taken system identification, as well as applied optimization. Applied optimization is a class offered in the math department, and it's a wonderful class. As controls engineers, we want always to try to optimize our designs and optimize our models, etc. We're always trying to improve. And so that's why optimization is so important. And then finally on this list, there is numerical analysis. Folks, anything that teaches you about using the computer and using models and doing simulations and doing analysis, mathematical and numerical analysis, is useful in the world of controls, in the world of machine learning, in the world of adaptive control, in the world of artificial intelligence. All right, let me say something about the master's. I already said everyone should get a master's. Folks, there's two paths here that you could usually take, and that one is doing a thesis. I recommend for anyone who really wants to learn a subject area and wants to become an expert in an area, I would recommend think about doing a thesis. Think about doing a thesis. It would be cool if you can tell your employer, your potential employer, here's my thesis, here's what I did, and it was a lot of work, and this is why you should hire me. That's very powerful, folks. Now, having said that, there is also the MSE exam, and which is just, an exam that you take, you answer questions, and we try to help the students out, give them an idea of what is going to be on the exam, at least the topics, etc., and so forth. And so it hasn't been too stressful to the students. But you can see I'm a little bit biased towards the thesis, but I should point out again that probably most students, not probably, most students do pick the MSE exam. But the thesis could be very beneficial to you if you're serious about learning a subject area. All right, I said this before, get your master's. And folks, I want you to get your master's not because you're going to make $10,000, $15,000 a year more, although I think that's kind of cool, but because it's going to open up doors, because it will allow you to work on cooler problems, because your employer will just treat you differently. They will view you very differently. They will put you in charge of stuff. You will be probably in charge of several others or maybe a team of others that are undergraduates, and the undergraduates with their bachelor's degree, they will be doing stuff for you. But the main reason for getting your master's degree, again, is not the money, although that's good, but because it will open up doors, it will give you tremendous flexibility. And most importantly, it will allow you to work on really cool problems. All right.
Professor,
Yes.
there's a question in the chat
Go ahead.
from Chris. It says, are there any neural network related classes for the undergrad?
Here's what I would recommend. That's a good question. So 511 is a graduate class in neural networks. Here's what I recommend. The question is, are there any undergraduate classes in neural networks? So strictly speaking, the answer is no. However, here's some options for you. Number one, you can go speak to Dr. C and ask her if it's okay to take her graduate neural network class as an undergraduate. Many of my senior level undergraduates have taken her class. This is after taking controls with me. All right. Another option that you have is that you can do an independent study with either me or Dr. C or Dr. Sakalis or Dr. Lang, and it can be on neural networks and machine learning or artificial intelligence or almost any topic you want. And doing one of these independent studies is something I recommend to lots of students on a regular basis, because you can really learn a lot. You can work closely with the instructor, and you can prepare for that honors undergraduate thesis, or maybe even that graduate master's thesis. And so students have leveraged one or two independent studies to prepare for the honors undergraduate thesis and the graduate thesis. Okay, any other questions? Okay, I think I've told you a little bit about the faculty and what they work on. Let me repeat, Dr. Lai and Dr. C both work on brain stuff and neural networks and machine learning. We all work on neural network stuff and machine learning stuff, but our experts on neural networks and machine learning stuff are Dr. Lai and Dr. C. Both of them work on brain stuff. Dr. Sakalis works on brain stuff as well as semiconductor ovens and other applications. Myself, Rodriguez, I work on all sorts of stuff. Biological stuff, chemical stuff, space stuff, things on the ground, things in the air, things underwater. If you've got an interesting problem, even if you come to me even with an uninteresting problem, I will make it interesting with you. All right, I think I just ran out of time. The job opportunities, folks, are all over the place. The list here is very, very long. Controls is everywhere. They might not call it controls. They might call it systems. Okay. They might call it cybernetics. They might call it, it might be cast in the world of neural networks and machine learning or artificial intelligence. But please don't be confused by that. If there is something out there that you're interested in that involves intelligent systems, then that means it involves feedback loops. That means it involves controls. And please don't be, know the following: 480 and 481 is the foundation. Okay. Now, can we entertain some questions?
Professor, there's a question. It says, not sure if this will be discussed during the presentation, but what are some active areas of research in controls, areas that might be appropriate for a PhD student?
Okay, so I have touched on lots of areas in what I've said, namely, driverless vehicles, drones, coordination of multiple robots. I've got students myself that are working on many robots on the ground, many robots in the air. I don't have anyone working on many robots or robots underwater. That's okay. In the air and on the ground is enough for now. Certainly in space. But there's semiconductor ovens, there is brain-powered prosthetics, and I could just go on and on and on. The list that I made of where is controls used is huge. It is a huge list. There it is. We can be designing an auditorium and trying to control the acoustics using advanced multivariable adaptive control and machine learning and yes, artificial intelligence. Okay, and optimization. And we could be controlling aerospace vehicles. And there's all sorts of aerospace vehicles, not just a spacecraft. It could be the planetary explorers, the rovers, robotic vehicles that go and get deployed on the planet and that are exploring the planet and that are gathering up specimens, that are analyzing the specimens and maybe even making a decision based on the analysis. And all of that decision-making fundamentally involves feedback and hence controls. Okay, and that's why, for example, capital investment, which is portfolio management, investing in stocks, bonds, etc. That's fundamentally a controls problem. All right, folks, any other questions?
Professor, there is another question from Vignesh Mani. He's asking that, are there any entry level of research opportunities available for freshmen for this subject?
Okay, so my advice to everybody, not just freshmen, but I have these discussions even with high school students. Talk to the professors. Well, first, go on their webpage, see what they do, then talk to the professors, meet with them, see if they can give you a project. There's a lot of stuff that you can get involved with and you can start learning about. If you are a high school student, a freshman or a sophomore, there's a lot of learning to be done. A lot of learning to be done. And certainly if you want to do any work in the area of robotics, drones, driverless vehicles, controls, artificial intelligence, then I would say, hey, learn the basic stuff really, really well. Remember what I said, it all started for me in circuits. And there's probably lots of people might even say, circuits doesn't have anything to do with controls. That is just not true, because circuits gives you a way of thinking. It's a way of analyzing, and that is fundamental. In circuits, you learn how to derive a transfer function. Well, it so happens there, the transfer function's for a circuit. But for me, when I look at a transfer function, it doesn't have to be for a circuit. It could be for a hypersonic vehicle. It could be for a missile. It could be for a semiconductor oven, etc. and so forth. So really learn the basics. But in terms of opportunities, go on the web pages of the professors, see what they're doing, see what you're interested in, dive in. And I would advise you to maybe even pick up some books and start looking. And there's a lot of stuff on the web that you can look at before you buy books. But at some point, you might want to pick up a book and start looking at it. And please don't get discouraged, especially if you bought the wrong book, right? Because it's very easy to buy a book. You open it up and you go, oh, crap, what did I do? Right? Because, you might get scared on chapter 1. Don't let that happen to you. Don't ever let that happen to you. Don't be scared. All of this stuff is doable by all of you. It's just a matter of finding the time and incrementally progressing from one step to the next. This stuff is doable. And I must say that, you know, this stuff, there's a lot of math involved. And when students see some of the math, they may get scared. Don't let that happen to you. Okay? Don't choose another career path because you get scared by something you saw. Now, dive in, get involved. And then after playing around with it, maybe for a year or so, maybe a couple years, then you can move on to other things. And if you dive in and you give it your all, whatever you learned there will help you with anything else that you do. So what I just said, folks, I work on a lot of projects and I am always thinking about what is my next project. Always thinking about the next project. And so whatever project I'm working on, I give it my all because I know it's going to help me with the next project. All right. Any other questions, folks?
Professor, there's another question from Patrick. He's asking that what applications of controls did Dr. Rodriguez use in the renewable energy project he did?
So by applications, you're referring to software, I guess. And certainly for basic so I didn't mention this in the presentation, but at the heart of all the analysis and numerical work that we do, we use MATLAB and we use Simulink. And then if we need to write code to run really, really, really fast, we will write it often in C++. And these go a long way. And for those of you that might think that MATLAB, that's like baby stuff or Simulink is baby stuff. Folks, when you build a system that has, let me see. So here, let me pick one. I worked on a program called SPICE. SPICE stands for Space Integrated Control Experiment. Now, what was this? SPICE, under the first President Bush, was a laser weapon system to shoot down missiles in space. When Clinton became president, we were still doing the same thing, but it was a space telescope. So instead of shooting missiles down, you were pointing very quickly and then taking a picture. But here's what was involved. The model that we were using had roughly, 300 to 350 differential equations. All of this was implemented in MATLAB and Simulink. It ran very slowly there. And so we implemented in C code to run much faster. So that is the answer to the question. And when we were working on renewable resources, we were using MATLAB and Simulink and C++. And there were other applications that we used, but those were the main applications. Any other questions?
Professor, there's another question that would you recommend pursuing a professional engineering license for the work in the control systems field?
All right, so the question being asked is, do I recommend getting a PE, a professional engineer license? So traditionally, civil engineering students that are graduating, that is what they're doing. It's needed for a lot of work in that arena, for work in the controls engineering, and for that matter, in any other branch of engineering, mechanical engineers, chemical engineers. Most of them do not get PEs. However, let me say the following. If you plan on having your own business and you're going to be doing work for the public, and folks, that means you better have good insurance because there's a liability there. all right? But if you're doing work for the public, then I would recommend having a PE. Now, having said that, there are probably, there might be hundreds. So there, I certainly know hundreds of engineering professors around the country, and they have companies, and they do serious work for companies, and they do serious work for the public, and they do not have a PE license. So I've done a lot of serious, so I've had a company for many years, an LLC, Control 3D, and I've done lots of serious work for many companies and for individuals, and I've never needed a PE. I've never even had an incident that suggested, okay, maybe I should have a PE. But folks, you know, if you're going to be going into people's homes and installing wiring and blah blah and rewiring stuff, and so then, you know, I would certainly think strongly about getting a PE and good insurance. Good insurance. Any other questions, folks?
Professor, there's another question from Kisha.
Keisha, okay.
Yes. Are there any research opportunities available for online students?
Okay, so the question there, are there research opportunities for online students? And I will give the same answer that I give for any student. Go on the web pages, see what you're interested in, see what the professors are working on, make an appointment to speak to them. It would be ideal if you could see them. You can maybe schedule a Zoom session. I'm reminded of the pandemic. We'll get through this, folks. We'll get through this. Unfortunately, it might take another year to fully get through this. And by the way, that's not just that is a professional opinion, not just something that I'm pulling out of the air. Okay, it may very well take a year before we really get out of this in some way that we can all refer to as normal. But again, I would say contact the professors, meet with them, speak to them, see what opportunities exist. And everyone is different. Everyone is different, and they might have something for you. These days, I think with everything that's going on, it's a little difficult, especially if you're interested in working with a professor, building stuff in her lab or his lab. Then that requires going to the lab and maybe working with people. And obviously the pandemic gets in the way of this. But folks, this can be done, and people are doing it, and people get tested, and people that have been tested work with each other, and people that are serious about their work, they might, you know, really seriously isolate themselves from risky interactions. And so it's doable, folks. All right, but certainly in time, more will be doable. So I hope that that answers your question about opportunities for online students. I know of professors working with some online students, but you know, that's a case-by-case basis. Any other questions, folks?
That would be all. There's no other new questions.
All right. Well, we've taken a lot of time. I hope that that hasn't disturbed.
Professor, I have a quick one.
Okay.
Yeah, I'm a undergraduate third year. I'm a student from Canada. I'm taking my course entirely online. So for a master degree, can be taken completely online as well?
That's a very good question, and I want to be careful in answering it.
I can help with that, Dr. Rodriguez. This is Bob. But yeah, we do have a fully online master's degree in most areas. So it just depends on your focus area.
Right, and my answer was going to be close to that. I think that we are very, very close to offering almost everything online. This semester, for example, my 588 class is being run from Zoom, so anyone would be able to take that. However, this question is one that really I have to defer to the administration to answer.
I just added the link to the chat so you can look more in depth. Just click that link. It'll give you what you need to know.
Yeah, I saw it.
Thank you.
Thank you very much.
Thank you, Robert.
Great. Any other questions?
Professor, there's another question from Patrick.
Okay.
So, can we say that controls field career is mainly a software intensive discipline with very little hands-on circuitry?
Okay, that's a good question, and you know, it's rare that I hear new. Usually, the questions I hear are questions that I've heard many times, but this question is a little different than what I'm used to hearing. It's a good question. There is a lot of software opportunities in the world of controls. I would advise all students, all engineering students. And I was advising students this 15 years ago, 20 years ago. Learn how to program. Learn how to program, because just programming by itself will keep you employed. It will not just only keep you employed, but it will allow you to do some pretty sophisticated stuff if you can write good code. It will also allow you to have your own business if you can write good code. Having said that, the answer to your question, strictly speaking, is no, in that it is not just software. There's a lot of hardware that can be done. Now, let me say the following. Certainly, I think we would all agree that there's more software to be done than hardware, right? Because for every piece of hardware, there might be 20 people or 50 people writing software for it. All right, so that's just the economics of hardware and software, the physics of it. That's just the way it is, the numbers associated with it. So there's always more software to be done. All right, but there's a great deal of hardware to be done in the controls arena if that is what you want to do. So if you want to build quadcopters, if you want to build robots that walk, one of my graduate students is listening to this presentation, Soham. He's doing his master's degree and he will be continuing for his PhD, and he is working on robots that walk and that run. And how about 100 robots that walk and run and that are doing things together? All right, so that will involve hardware and it will involve software. Now, when I say software, I want to make that clear that there's not, I mean, there's a lot of coding to be done, but it's not like you're a software programmer per se. Controls, if you're in the world of controls, then you're there and you're getting paid a lot of money because you're there to do analysis based on models and design based on models. And then after you do this analysis and you do the design, then and some of the design work takes place in MATLAB and Simulink. So there's coding to be done there. All right, and so the two go hand in hand. So I wouldn't refer to that strictly as just coding. I mean, I can write C code, and I can write code in any language if I really want to, but I certainly don't call myself a programmer per se. All right, that's not what I see myself or I see controls people as. With that said, I hope that answers your question. Any other questions?
Professor, there's another question from Chris. Um, would you ever recommend the electrical contracting route? Yes. The question is, would you ever recommend the electrical contracting route after completing EEE undergrad program?
So when you say electrical contracting, I'm not sure I fully understand what that means. If that means, so if I'm missing something, please let me know. But certainly if that means having your own company and doing consulting, I recommend that highly, very, very, very highly for any engineering student that wants to evolve into a very productive engineer. I recommend doing consulting and doing contract work, etc., so forth. Many companies got started doing that. Many companies. Most companies got started doing some type of contract work. Okay. Now, if that is not what you meant, please rephrase the question and I'll do my best to try to answer.
Yes. So yes, he mentioned he meant that to become a state licensed electrical contractor acting as a subcontractor on construction projects.
Okay, so certainly if you're going to be a subcontractor on construction projects, you know, I would think seriously about getting your PE license. Certainly. There's a great deal to be done in that arena. Now, I will always tell students, regardless, get your master's degree. Get your master's degree, and again, not because you'll make $10,000, $15,000 or more, but because it will open up doors, it'll give you flexibility, you'll be able to work on cooler problems. And yes, here's one that I left out. When the layoffs come, and folks, layoffs always come, if you have that higher degree, then they will think a little bit more about whether they should let you go or not. Most high-tech companies rely fundamentally on brain power. And so folks, learn as much as possible, dedicate yourself to your classes, and dedicate yourself to lifelong learning. You're going to be learning forever, folks, and that's a cool thing. That is a wonderful thing. The thought of me not learning, oh my goodness, that's depressing. That's really depressing. I often have problems going to sleep because I look forward so much to what I'm going to be learning the next day. And, you know, after this meeting, I'll be talking to one of my students about walking robots. Any other
Yes.
questions? Are we done?
Yes, there are no questions for now. Yes.
All right, then I think that I've probably not just exceeded my time, but I may have gotten some people upset. I apologize, but I hope that this was useful, and I hope that this will be useful to students that watch the video in the future. Again, I want to wish everybody the very, very best. Please stay safe. I want to wish you and all your families the very, very, very best. And if you want to reach out to me, I'd be eager to talk to each and every one of you about anything.
Thank you so much, Professor.
Okay. You take care, folks. So
Thanks, Dr. Rodriguez. Thanks very much for contributing today.
All righty. And I guess you or Cheryl will be shutting down the recording, or?
Yep, I got it.
All right. Thank you so much. Take care.